Hello everyone. So in the previous session of operating system, we spoke about hardware support for page table, memory protection, and shared pages. So in today's session, we are going to talk about the structure of the page table and segmentation. Okay, so basically when we looked into the diagram where the page table looks something like this, where there's a mapping between page number and the frame number, right? So how is this structured? How is this page table structured? Is it one contiguous memory location which is having this data, or is it being designed in different way? So let's try to understand that. Memory structures for paging can get huge using straightforward method. So if I just say there's a mapping between page number and frame number, and that is one contiguous way, then it will be very huge if you consider for a higher bit processor, right? So if you consider a 8-bit logical address, okay, which is produced by the CPU, 4-bit is the size for each of the page. Let's say 4 bytes for the size of each page, and they are basically 4 bits to represent the number of pages. So what does it mean? Each page, okay, each 4 bits of this one can have a size of 2 to the power of 4 page. So that is basically the offset is 2 to the power of 4, and page number is 2 to the power of 4. Right? So when it's 2 to the power of 4, so it means each page has to have one entry in the page table. So basically there will be 16 entries, 16 entries within this particular page table. So 16 entry is not a huge page table. Now let's move to a 16-bit logical address, considering the page size is of 2 to the power of 4. Okay, so what is the page number size? It is 2 to the power of 12. Okay, so 2 to the power of 12 means almost 14 KB, that is 4000 bytes. So this page table will be decreased from 16 bytes to 4000 bytes if in case the logical address is changed from 8-bit to 16-bit. So that is also quite manageable to store a 4 kilobytes of data in the main memory, which is basically to occupy the page table. Now let's move on to modern computers where the logical address is basically a 32-bit or it is 64-bit. So let's consider 32-bit logical address. Okay, so in this 32-bit logical address, let's consider 12-bit is basically for the offset. So 2 to the power of 12 is basically to represent the offset address, and 2 to the power of 20 is basically to represent the page number. Okay, so if 2 to the power of 12 is for offset, and the page size is basically, so total is 32, right? So 32, among 32, 12 is for offset. So what are we left with? 2 to the power of 20, which is almost 1 million or 1 megabytes. It means this page table will have 1 megabytes of data just to hold the configuration or mapping of page number and the frame number. That is quite huge, right? So if you imagine a main memory itself, which is almost a few megabytes, in that few megabytes, if you're taking 1 megabyte for just to have the entry of page table, that is quite consuming a huge consumption of physical memory, where basically it would want the processor to processes which has to be processed by the CPU to be placed on the physical memory. So this page table shouldn't be huge in size. It has to be resized such that the size is quite considerable enough to place it inside the frame which is there within the physical memory, right? So this page table shouldn't be huge in size. Okay, so what is so that amount of memory used to cost a lot, they don't want to allocate that continuously in the main memory, right? So if you're telling you want 1 megabytes of space just to save the page table information, then you really looking for some continuous memory allocation, and that won't be possible in the to place it onto the physical memory. So how do we deal with having the page table being in a different structure? Okay, so basically this is just an example of this scenario where I'm considering a 32-bit logical address, 12-bit it's for offset. So So that process, let's say a process is 2 to the power of 32 bytes. Number of pages, right? So number of pages will be basically 2 to the power of 32 by 12, 2 to the power of 12, that will be 2 to the power of 20. So it's basically means you require 1 million bytes of data just to store the page table. So if you look over here, this page table is requires 1 million entry. Okay, let's say each entry is around 4 bytes. Basically, page table is mapping between page number and frame number. Let's say it has other information, like we spoke about memory protection, right? 1 bit for memory protection. So assume there are 4 bytes for one entry into the page table. So this 4 megabytes, sorry, this 1 megabyte for entry in the page table into each size, that is 4 bytes, will require 4 megabytes. So the page table length itself 4 megabytes. Okay, there's no useful instruction. It is just the mapping between page table and the frame number, where the size is very, very huge, right? So how do we take care of breaking this page table into a smaller structure so that it can be placed within the frame of the physical? This is the physical memory and this is the page table, right? If you see here, page size is 4 megabytes, but here I'm telling it is 2 to the power of 12. It's nothing but 4,000 bytes or 4 kilobytes, which is a small size, very much small size compared to the page table size. So the structure of the page table can be done in various ways, and few of the way that is to be discussed is the hierarchical paging, hashed page tables, and inverted page tables. So let's try to understand each one of them. Okay, so the basic structure looks something like this, right? It looks something like this. Processor reduces the logical address. You take the page number, look out for the frame number, take the frame number which basically has the base address, add the logical so displace offset that is part of the logical address, and you get the physical address. So this was the basic structure we understood, and there is one page table. If this page table is very huge, you can do the hierarchical paging concept, where the logical address is broken into multiple page tables. So what basically hierarchical is, you have a relation of a parent and child, that child having another child. So there is a kind of relationship between the outer parent and the child. So here, why don't we create a relationship such that the logical address space is broken into multiple page tables? Okay, so the simplest technique is the two-level paging. Instead of having one level of page table, why don't you break it down to have two level of page table? So what do you mean by two-level page table? So previously, if you remember, we took the 32-bit logical address and we said 12 is for offset and 20 is for the page number, right? So naturally I said uh, here okay, here I've slightly changed it. Considering the page offset is 10-bit, naturally the page number will consist of 22-bit. So it means what? 2 to the power of 10. 2 to the power of 10 is nothing but how much? 2 to the power of 10 is 1 kilobytes, right? So each page can have a each page can be of a size which is basically 1 kilobyte. Okay, and how many pages, how many such pages can be there? It's nothing but 2 to the power of 22, right? In the previous example, 2 to the power of 20 itself was giving up to 1 million bytes, 1 megabytes. So 2 to the power of 22 is even more bigger compared to the 1 megabytes of data, 1 megabyte pages, right? So what do we do? So since the page table is page, the page number is further divided. This 22 bits of page number can be divided into 12 bits and 10 bit. Okay, so 12 bit, I mean this page number is further divided into 12-bit page number and 10-bit offset. What does it mean? Each page number which is of first 12 bits is mapped to the other 10 bits. So they have just given, we give it as page offset. It is page offset. Okay, so mapping between this page number to its particular offset. Okay, so the logical address can be changed as 12, 10, and 10. So this page number is divided into two sections. One section having 12 bits, another section having 10 bits. So each 12 bit is mapped to all the 10 bits in the second section. P1 is an index to the outer page page table, and P2 is the displacement within the page of the inner page table. Okay, so this is nothing but the offset. Forget about the offset. You're basically seeing that the page number is being divided into two sections. So each 12 bits of P1 is mapped to each 10 bits of P2. Okay, fine. So totally how much it will be? 12 into 10. So naturally each 12 bit plus 10 bit will give you nothing but 22 bit. So now if you see, right, so 2 to the power of 22 was greater than 1 megabyte. Now, what is 2 to the power of 12? 2 to the power of 12 is nothing but 4 kilobytes. What is 2 to the power of 10? 1 kilobyte. So you can see the size is 4 kilobytes and here it is 1 kilobyte, which is very, very small compared to the 1 megabytes of size for the page table, right? So this is also known as forward mapped page table. Okay, so if you look at the diagram, it would look something like this. Two-level paging, two-level page table scheme, where you have the outer page table and the inner page table, and then you have the physical memory, right? So previously you saw there was a table and directly looking up to the physical memory. But here in this case, you have two page table, outer page table and inner page table. If you consider this example, what is the bits representing each page table? Here it is 12 bits and here it is 10 bits. Each 12 bits of the outer page table is mapped to each 10 bits of the inner page table. 12 plus 10 will be 22. So that address is considered and looked up onto the physical memory. Okay. So here, what will be the size of this? It will be 4 kilobytes and this size will be 1 kilobyte. Here it's looking big, but if you take this example, the size of this is 4 kilo and this is 1 kilobytes, right? Which is very, very small compared to one single 2 to the power of 22, which is very greater than almost 4 million bytes, 4 megabytes. Okay, so this is how you can basically have a two-level paging for a 32-bit machine. Okay, for the page sizes 1 kilo, right? So if the page size is 1 kilo and assuming the frame size is also 1 kilo, how many frames would you require over here? 4K for this and 1K for this. So totally how much? 4K for this, 1 kilo for this, and 1 kilobytes for this. So 4 plus 1, that is 6. So if 1 kilo is 1K byte is the size of each frame, basically you would just require 6 frames. So 6 frames are good enough to hold the information of this outer page table and the inner page table. Okay, so this is with respect to a 32-bit logical address. Okay, and you can pictorially show it in this way. The logical address is P1, P2 and displacement. So these two forms the page number, where the outer page number is represented by the bits what is shown over here. In our example, it is 12 bits. Each 12 bits is looking up to the 10 bits of the inner page table. So this is the outer page table and inner page table. So combination of this and this will, you have to take the displacement, okay, and add it up to that particular frame number and you will get the physical address. Okay, so this is the diagram of the address transition scheme and address translation scheme. So is it clear? So here I have a two-level paging. Okay, what do I mean by two-level paging? But the page table is divided into outer page table and an inner page table. Now let's think of a 64-bit logical address. Okay, so in the 64-bit logical address, okay, if I implement this outer page and the inner page, assuming that the offset is 2 to the power of 12, which is nothing but 2 to the power of 12 is almost 4 kilobytes. Assuming here I took it as 1 kilobyte as the page size, right? Here I'm telling each page is almost 2 to the power of 12, that is 4 kilobytes of size. So what will be the logical address, which is nothing but 52. Okay, so this 52, I break it down applying two-level page table scheme. In that case, if I consider the outer page to have 42 bits and inner page to have 10 bits, you will see 2 to the power of 44 is even quite big enough. It is again, which is of more than a huge megabytes, or it could be lead to a terabytes of size of page table, which is very, very huge, right? So if a page table is 2 to the power of 12, then the page table entry would be 2 to the power of 52, okay, which is very, very huge. So what can you do? If even if this two level paging is not good enough, because the size of the outer page table will be very huge, what you can do is you can still break it down in such a way that outer page table is further divided into two sections. That we call it as a three-level paging scheme. So this is a two-level paging scheme. When I break that down into a further three-level paging scheme, where the offset is remained the same, the inner page is 10, outer page is further divided into second outer page and the outer page. So this 42 is divided into 32 and 10. So what would be the size for each of the page table? I mean, the page table now, it would be 2 to the power of 10. That is nothing but 1 kilo. Here again it is 1 kilo, but this is also a quite number. If you take 2 to the power of 32, the size of the page table will be very, very huge comparatively to the two level logical address. Here it is the page table size would naturally decrease. Okay, so here you see this page table size is quite huge enough, right? So if in a 64-bit logical address space, applying a three-level paging scheme is also will lead to a page table which is very huge to be placed onto the physical memory. So there are other structure of the page table we can understand, and that is basically the hashed page table. Okay, so we are done with the hierarchical page table, where basically the page table can be a two-level paging or a three-level paging. Two-level paging is good enough for a two-level, or a three-level paging is good enough for a 32-bit processor. But for a 64-bit processor, the page table is again in a very huge size, right? So if for a address space which is greater than 32-bit, we make use of the hashed page table. We'll look into the diagram and then talk about it. So previously in hierarchical, this page table had two or three level, depending upon whether it's two level paging or three level paging. Now what happens, that page table will be called as a hash table. Okay, so what happens over here, once the processor produces the logical address, which is a combination of what, page number and offset number, right? So this page table, on the page number, we apply a hash function. There are n number of hash function, multiplication hash function, division, and so on. Okay, based on the requirement, we take that particular hash function. Once that hash function is applied on the page number, okay, so that is being mapped to the corresponding frame number. So where that process page is being lying on the physical memory, that map is done and placed onto the hash table. Okay, so does it mean for each of the page number there is a hash function being applied and the entry goes on? So that almost will be equivalent to having a normal page table. How is hash table different from a normal page table? So here, apart from the hash function, we also have the linked functionality which is incorporated. Okay, so each of the hash function value will be mapped to an array of linked list arrays. Okay, so what happens over here, each entry of the hash function will be linked to each element of the linked list. Okay, so let's go back. So what happened, the page number, on the page number we apply the hash function, and here they call it as a virtual page number. The virtual page number is hashed onto the page table. This page table consists of a chain of elements hashing to the same location. So what happens to the same location? Okay, to the same location, let's say page number of different process is been hashed onto that particular location. Each element consists the virtual page number, the value of the mapped page frame, and the pointer to the next element. Virtual page number are compared in this chain searching for a match. If the match is found, the corresponding physical frame is extracted. Okay, so now what are they telling? Internally, okay, when you apply the hash function, okay, internally there are three values being stored: the hash function value, the frame number, and it would be null if in case there is no link to this particular array. If in case there's a link between the first array and the second array, then here the address of the next array will be specified. Okay, let's say there is, you're looking, let's say this is for page number 1 and this is page number 2 of a process. Okay, let's say I produce a logical address of page 2. Okay, so there's a hash function that is applied on page 2. Okay, and here you're going to pass on that particular hash value. That hash value is checked if the mapping of that hash value is done for that particular frame number. Second value is a frame number. If the hash value generated and the frame mapping is mapped is equal, then that will be the physical address. Okay, but now I'm telling this is page number 1 and this is page number 2, and logical address what is generated is of page number 2. So once the hash function is applied on page number 2, okay, you're going to check if the hashed value of 2 is mapped to this particular frame number. So naturally it would not, because this is the linked list array of the first particular uh, page. So the address of the second linked list is being provided over here. So once you go to that particular linked list address, you're going to see if the hashed value, what is generated, and the frame number is mapped in the second array. If so, that particular frame is taken and you take the offset that is generated by the logical address, and that you produce a physical address, which you're basically looking for the second frame, because the second page is mapped onto the second frame. Okay, anything, it need not be second frame, to whichever frame it is mapped, that frame is taken and the offset is being added, and that generates a physical address. Okay, so in this case, instead of having the what is it, the entry for each page numbers of each process, you apply the hash function, and for each hash function you have a linked list that has been assigned. So once that mapping has been mapped, only then you consider the corresponding frame number. Okay, so that is the importance of the hashed page table. So here you will see the hash page table size is very much small compared to the a normal page table, where each of the process page table will be there, and that is a very huge in size. Okay, here, though, I mean, it depends. For each process, you have one hash function that has been applied, and then you look into the corresponding linked list. Okay, so that is what is being told. Each element consists of virtual page number, the value of the mapped page frame, and the pointer to the next element. If that virtual page number and the mapped frame is not right, then I go to the next element. Okay, so in this case, I am telling I mean, here each entry over here is for one page. Okay, so if there is second page process coming, the page number is again mapped to the same thing. So what if in case, if you have large number of data, I mean logical bit address, in that case you can make use of the clustered page table, where each entry can look up to several pages rather than one page. Okay, so here you can just assume for each process you have an entry. So in that case, in previous scenario, that hierarchical page table, each page has an entry. Okay, here you can consider each process has an entry in the hash table. So if there are 10 processes, there will be only 10 entry. Okay, so there will be 10 entry. So this hash function will be based on the process. Okay, hope it's clear. Okay, so that is about the, so depending upon the number of process, you have so many entries in the hash table. Next, we move on to the inverted page table. Okay, so here, rather than each process having a page table and keeping track of all the logical pages, track all the physical pages. So here what I'm telling, let's say there are two processes. So as soon as two processes has been placed in the virtual memory, okay, let's say two processes has been executing. So instead of taking the, instead of having the page table of the entire two processes, okay, process 1 and process 2, why don't I keep the information in the page table only the frames that is moved, only on the pages that is moved on the physical memory. It means if there are 10 pages for process 1, out of the 10 pages, if only 5 pages is there in the physical memory and the rest 5 pages are there in the disk, why do I have to why do I have to keep the entry of the entire pages of that particular process? I track only the physical pages which has been present on the physical memory. So one entry for each real page of memory. Entry consists of virtual address of the page stored in that real memory with information about the process that owns that page. Decrease memory needed to store each page table, but increases time needed to search the table when the page references occurred. Use hash table to limit the search to one or at most a few page table entry. TLB can. So what it means is, so take this example. So let's say this is process 1 and process 2. Okay. So page table would look how? Page table would look like this, where page 0 of process 1 is mapped to first frame, page 1 is mapped to fourth frame, page 2 to third, page 3 to 7. And look at the page table of the process 2 J, again 2, 6 and 5. So what are these? These are the frame numbers. So I'm telling, if this process comes onto the main memory, these are the corresponding frames that has to be looked up to. Okay. But if you look into this physical memory, page 0, page 1. These two are of process 1. Page 1, page 2. So actually the physical memory does not contain the entire process 1 and process 2. It's just having 2 pages of process 1 and 2 pages of process 2. So why don't you keep a track of only these uh, frames which is occupied by that particular pages of that particular process? That we call it as inverted page table structure. Okay, so here instead of having page table of maintaining all the thing, now I'm saying page 0 and page 1, it is in frame 1 and it is in frame 4. The page 2 and page 7 which has to be moved on page 3 and page 7 which will be moved over there, that is still not moved on to the main memory. Okay, that mapping is done, but it is still not moved on to the main memory. I say this is still there in the disk. So instead of keeping the entire track of all the page number and the frame number mapping, keep the track of the ones that is just moved on to the physical memory. That is what is inverted page table structure. So here if you can see, and here there is one more addition to the logical address that is being generated, because the reason is, see, page process 1 also has page 0, process 2 also has page 0, right? So if I look over here, this page 1 and page 1, to to which process does it belong to? That I can come to know only if I have a prefix of which process ID. That is why if you look into the architecture of the inverted page table, the logical address that is generated by the CPU has process ID, the page number and the offset. Okay, so inverted page table will have, look at this, the table will look something like this. You have the process ID and page number. Okay, for this process ID and page number, what is the corresponding frame number? Okay, see page number, here it is 1 and 1, but this page number is for which particular process ID? So if you know 1, it means 1 and 1. First process, page number 1 is mapped to 4. Though there are 4 pages for process 1, only 2 is there in the physical memory. So only those 2 entries are there in the inverted page table. Okay, so I take up the combination of process ID and the page number and pick up that particular frame. Okay, so that will be that particular frame. Okay, you add the offset and that will give you the physical address, or it'll tell you which frame it is basically which frame you're basically the processor CPU have to look up to. Okay, here in this case, the logical address and the physical address conversion is done with the help of the inverted page table, which has the information of process ID, page number, and the frame number. Usually it was just page number and frame number. Here I'm going to have process ID also, because the page number would repeat for each of the process. Okay, sure. Only which entry is there in the physical memory, only that is being information is there in the inverted page table. Okay, so that is what each entry of the virtual address of the page stored in the real memory location with information of the process that owns that particular page. So which process owns that page? So the entire information is there in the inverted page table. So naturally the page table size, which will be very, very less compared to the, considering the page table of the entire process, where which could have lots of page numbers within the process. Uh, if you consider this example, actually the page table should have 4 plus 3. How many? 4 entries in the page table. But here in this case, I'm considering only 4, because there are only 4 frames that is filled by process 1 and process 2. Okay, so this is about the inverted page table. Okay, so we went through how a page table can be structured. You break it down in hierarchical way, or you apply the hash function, which will naturally decrease the size of the page table, or you apply the inverted page table, where it concentrates only on the physical pages that is physically moved onto the memory. Okay, the physical pages that is really existing on the memory is considered, only those information is placed in the page table, which we call it as a inverted page table. Okay, so that's about the structure of the page table. Next we move on to the concept of segmentation. Okay, so what do you mean by segmentation? Okay, so there are a few things that you have to understand the difference between paging and segmentation. In paging, let's do diagrammatically. In paging, we made sure that process is being divided into fixed size page. Okay, let's say if it's 4 kilobytes, let's say a process is 10 kilobytes, 4 kilobytes is one page, 4 kilobytes is second page. The third page is 4 kilobytes, but out of that you are occupying only 2 kilobytes. Okay, so here when I say a process, it's nothing but a program. So when I think of a program, it has a structure. Let's say think of a simple C program. It has a header file, it has the main function, then you have the variables, you have the main global variables, etc. It's a stack, etc., etc. So when I say a program, it has a kind of structure within which we build up a program. So when I give a restriction saying that the process has to be broken down in a particular size, then they could be in such a way that you have header file and the main function over here, and you have few variables declared in this section and other variables declared in the next page. So you can see the paging concept doesn't divide the process into a very structured way. Okay, so that is when we consider the segmentation. Okay, so when we say the program is a collection of segments, is nothing but when I say segment, it could be main program, it could be procedure, function, methods, objects, variables, common or the shared block, stack, symbol table, and arrays. So they could be various units within a one program. Now, when we have this program broken out based on these segments, then it makes more sense, right? So it means if you're moving the main program, or let's say a procedure is one segment, you have the entire code of that procedure in one segment, instead of having broken down, because if broken down such a way that partial of the procedure should not be in the second segment, or so called the paging, right? So what happens in the segmentation, the program or the process is broken based on the segment, or the segments which has been defined as, what are those? It's nothing but one among these. So if I say process A is broken into pages, let's look at this. Let's say this is also on process A, and that is broken into 5 segments. This, let's say there are three, this process is divided in 3 pages, but here it is divided into 5 segments. What are the segments? Subroutine, square root 1 function, main program, symbol table, and stack. So according to the viewer, if he is applying paging concept, it looks something like this. If I apply the segmentation, it would look something like this. Okay, so this makes more understandable or more performance oriented, because you have the entire unit or the entire logical unit being separated into segments. Okay, so according to users view, paging looks something like this, whereas the segmentation looks something like this. Okay, here it is a fixed size, here it is not fixed size because the program or the routine size might vary. Users view, it looks something like this. So if you look at the logical view of the segmentation, if there are 4 segments, you can say each segment is placed in different location. And is the size of the physical memory the same? No, it depends upon the what? Size of each of the segments. So here you can see the segment third is huge, and naturally the size of that particular segment which is placed on the physical memory is also huge. So here the frame is not the same as the page number, page size, how it was in paging. Here it would vary based on the segmentation. This is the logical view. Now, how do we come up with the building up the hardware unit for the this particular segmentation, right? In the case of the paging, we had the hardware unit built. Let me show you. So it looked something like this, right? You had something like this, right? Like this. Now, how do we build up the hardware unit for the segmentation? Okay, so in the segmentation, let me show you the diagram. So the segmentation hardware looks something like this. Okay, the CPU doesn't produce, the CPU produces the logical address. In previously, I said logical address was a combination of what? It was a combination of page number and the offset. Here, the logical address that is generated by the processor is basically the segment number and the offset. Okay, so the logical address that is generated is the combination of S and D, that is nothing but segment number and this one, the displacement. Now, previously we had something called page table, but now we have something called segment table. For each of the segment number, okay, it gives you what is the size of that particular segment. Okay, clear? So what is this? The segment table has information of segment number, what is the size of the each of the segment, and from where is it, what is the starting address of that particular segment. Okay, so what is the segment table having? Segment number, segment size, and what is the starting address of that particular segment. So those 3 information is there in the segment table. And the logical address is a combination of segment number and the displacement. Okay, so now, so theoretically, if I say logical address consists of segment number and offset, segment table maps 2-dimensional physical address, that is the base and the limit. Limit specifies the length of the segment. Base contains the starting physical address where the segment resides in the memory. From where, what is the, here, this one, for what is the point, this particular, let's say if I say 4, from where is it starting? So that is nothing but the base value. So there are 2 registers, basically segment table base register and segment table length register. So this length is put over here and the base value is put over here. Okay, so if you look at this hardware diagram, for each segment pick up the limit and the base. So those 2 values is placed in the 2 register we just spoke about, that is the segment table base register and segment length register. So the length and the base is put in those 2 table. And then what do? You check if the offset that is being part of the logical address is less than or equal, is less than the limit. If the naturally I said when I say offset is nothing but the size of that segment, right? So just check if the one which is generated by the CPU is less than the limit. If yes, add to the base register value, and that will give you the physical address of which segment you are basically looking up to. If no, if the address is not, let's say if segment 1 and let's say size is 10, if it produces the address 11, naturally the size is greater than the limit value, then it will throw an error, which is taken care by the operating system. Okay, so in this diagram you basically have to understand the address that is generated is a combination of segment number and displacement or offset, and segment table has a information of what's the segment number, what is its size, and what is the starting address of that particular segment. Now let's understand this better with the help of an example. So here if you see, there are 5 segments: segment 0, 1, 2, 3 and 4. So the size of each segment is different. Now let's take the segment table. Okay, and this is a physical memory. Now since the length is variable, how do I make sure I start from this location and end up to this location? Let's take segment 0. If I look up, let's say logical address is 0, let's say logical address that's generated is 0, segment number is 0. So you go to the segment table and go to the segment 0 number and see what is the value, that is limit value and the base value. So limit is 1000. It means the size of the subroutine is 1000 bytes. From where is it starting in the memory? That is nothing but 1400. It means if you look up to the memory starting with the base of 1400, it means the segment 0 is starting from that particular base address. Until where can it go? It can go up to 2400 because the limit is 1000. So 1400 plus 1000 will be 2400. Any address which is greater than 1000, if in case I say I give 3 values: 0, 1001, 1400. Okay, so which is the segment it is referring to? 1000. Sorry, segment 0. What is the limit? It is 1000 and base is 1400. But let's say the logical address that is generated is 1000, offset is 1001. So is that greater than 1000? Here you can see, is it greater than 1000? Yes, here it is less than. If it is greater than 1000, then it is a error. So the address that is generated or the offset that is generated should always be less than the 1000. So it starts over here and ends over here. Let's take segment 4. Segment 4 is limit is again 1000 and it's starting at base address 4700. So it's starting at 4700 and it will end at 5700 because the limit is 1000. Okay, so the mapping between the logical address and the physical address can be done with the help of the segment table, which will give you the information of the size of the segment and what is the starting address of that particular segment. Okay, so this is so here there is no restriction of having the segments to be of particular size. This is more efficient. Let's say the stack 3 is over here, limit is 1100. Here, this one. Now here you see entire stack information is there in one segment itself. But if you had considered paging, maybe I could have divided this segment stack information into 2 or 3 pages, right? So here the entire stack information is there in the physical memory. So accessing it will be easier instead of breaking down into pages, because there you require context switching, right? From one page to another page you have to move. There is time taken from moving from one page. I mean, because the logical address will naturally change, right? Because logical address is combination of page number and offset. So if I have stack information in 2 pages, after information fetching from page 1, if I move to page 2, then actually the logical address will change, right? So there the context switching or the conversion from logical address to the physical address will be in a lesser, will happen will take some time compared to the segmentation, because the entire information is there in one particular segment. Okay, so this is about the segmentation. Okay, so segmentation, nothing but instead of having divided into pages, I divided into segments, and now have the hardware unit designed in such a way that the logical address is a combination of segment number and displacement. Based on the segment number, my segment table. Okay, in segmentation, I have segment table. In paging, I have the page table. And what are, you have only page number and frame number, or it could be the base address. Here I have again the what is the segment number, what is the size of it, and what is the base address. Okay, so this is about the segmentation and the corresponding segmentation hardware. Okay, so again, this segment table again can be improvised to have protection bit, all those things. Okay, so in today's session, we covered the concept of structure of page table and segmentation. Structure of page table could be hierarchical, hashed, or inverted. Segmentation, we looked up how the hardware would be different compared to a paging, where the paging had a different hardware support than compared to a segmentation hardware. Okay, so we complete this session. And if there are some problems related to any of these segmentation, I would be working out for the next recording. Thank you.